a wonderful meeting. This is going to be a whistle-stop presentation. I'm sorry for that, but what I'm doing is I'm inviting people to take part in breakout sessions and hack sessions and so on. So the details are not in here. Don't worry about all of that. So let's see if this works. Present a view. Okay, can you see that all right?
Perfect.
Right, okay. So I think that we should think of chemistry and materials as a language, a natural language. In this way, we'll find that what we talk about at the moment starts to fall into the tools that we need to organize it. Some points at the beginning: all my code is open. Well, it's not all mine. All the work is open notebook science, so everything is already up on the web as it's done. And the goal is to make the current literature semantic. Now, that's a huge goal, but I think it's possible. In other words, we should be in a position where we can read the current literature with machines helping us at the same time. I've put forward some ideas for hack projects and taken the mantra of the IETF, rough consensus and running code. In other words, this 80% satisfactory. I'm very indebted to a group of plant scientists in India that I've worked with over the years. We spend most of our time on semantic plant science. We had a break for open virus for COVID, but we've now taken a week or two to produce a presentation for MADISes. So these are the questions I think we need to ask at the beginning. What are the names that we use in talking about materials? What do the names mean? What are the objects that they're talking about? And I think very much in terms of objects. And what are the values of those objects? And I'm going to give 2 or 3 of our tools here that show how we can do that. We can go beyond that to linked data, but I think linked data is hard. And if we describe our objects well, then we probably won more than half the battle. So here's a typical bit of chemistry. Lizanne Hawisi from my lab in Cambridge did a brilliant job of writing a parser for this. I would demonstrate it, but we don't have enough time. But it goes into the machine and it comes up with this parsing here. And all of the material in this paragraph is completely parsed. The molecules are made semantic, the quantities are outlined, all of it is held at that stage in CML. And that was 12 years ago, and it's still working. So we can do it, it's a question of will. So I took the same tool, I put some materials into it, and that's what I came up with. That you can see it gets about half the words in there, but there are clearly things that aren't, like solvothermal and co-precipitation and things. We need to make dictionaries for these terms, because then we will have a tool which can turn this into semantic form. Now, I'm working with a wonderful group of young people from India. They're not material scientists, they're a mixture of plant scientists and computer scientists, but they've built this system. And Shweta and Ayush and Anuv, I hope, are listening into this. And this is what they've put together: a complete workflow where you can take papers, you can read them into your machine, you can break them into sections, you can analyze them with dictionaries using natural language processing and come up with key phrases. And you can process perhaps 1 paper a second, depending on being polite to your server. So here's a typical example from Ayush. We look for X-ray fluorescence spectroscopy. You can see even in PubMed Central, which is a bioscience repository, we get 40,000 hits. So if you want to do exploratory stuff, you don't have to worry about it not being in there. And I think PMC is really taking most of the open access material in anyway. So this is how we split the paper up. So this paper was a PDF turned into XML, and every single section in that has its own labeled paragraph or subsection there. And so we can look into metadata, text, captions, tables, and that's all automatic and takes a second. And Shweta put this together for using a tool called SciSpaCy, which is a Python tool, open source, of course, and look for phrases. And these are the types of phrases that it came up with. And this had no hints whatever. This says that these are the most important phrases in those papers. So you can obviously see it's about X-ray spectroscopy. And every single instance in the paper is located. Here are some of the things it came up with. And what we've done here is linked it into Wikidata. And I hope you probably now have heard that term several times, but it's now the largest collection of metadata and data formalized on the open web. And so you can see here it's picked up elements, it's picked up X-ray techniques and so on. Another student, Prachi, put this together last year. So we make what we call dictionaries, download the literature, and then we search it and link it to Wikimedia. Here's how we create dictionaries. We ask a question of Wikidata using Sparkle, automatically gets turned into dictionary, and we can use that dictionary. We have many, many dictionaries. You can have hundreds of dictionaries, each for each subtopic of your discipline. Don't be afraid of Sparkle. This is Wikidata using Sparkle. These may be opaque, but it's got a tool that tells you that P31 is instance of, and Q59447 is diterpy. So that's how you ask a question, and within less than a second, you get all the diterpenes in Wikidata. Here are some of them. And you can then, with our software, put that together in a dictionary. So this is now a dictionary of terpenes, each with their Wikidata ID. And the most important thing for any piece of information is to give it a unique permanent ID. If you can do that, you've won half the battle. And a typical dictionary looks like this. We're very keen on global equity. English is not the only language of publication, and this is a multilingual dictionary. Although it's got English as its term here, you can see synonyms in English here, and then many other languages here. There's a huge amount in Wikidata. There's not enough in material science at the moment, but here are some examples. Modulus of elasticity, P5480, and here, and a shout out to the Crystallography Open Database who are with us here, that this is an identifier for structures in that database. So I'm also working on a project on battery materials with Matthew Dunstan in Cambridge. And this is a typical dictionary you put together, anode, cathode, current density, all of them linked into Wikidata with their description. It's not rocket science, but it's incredibly powerful. So we're now going to look at using it for search, annotation, and mining. We've broken the paper up into different sections, as I showed you, and we can use different dictionaries for different sections. We can look specifically at the image caption or the table captions. And here's an example of a search. So we're looking at the methods section for the chemical elements. And you can see here it's found lithium, and this is its context. And this is the W3C spec for annotation. So that will work with W3C tools. And lastly, we've shown how we can do text. I'm now going to show you how we can extract data from diagrams. So here's a diagram, which I started looking at a week ago. can we extract all the data in this? There are 500 pixels across here, each corresponds to a data point. So we can automatically extract it into a CSV file. So that will give you 12 CSV files for this one, 12 for this, and they will all be labeled as this, and this will be labeled in Wikidata. Now, I'd hope to be able to show it you now, but I will certainly be able to show it to you probably tomorrow. Just to show we can do it, this is a data from another project, it's astrophysics, but a typical plot contains a plot with lines and points, and then two axes with tick marks, numbers, quantities, and units. And if I run the tool on this, here we get a dumb PDF, it's turned into a CSV file. So there are 2,000 points from that PDF, and you can do experiments, and I've shown how you can do, you can smooth the thing here, and you can also work out the noise by looking at the second derivative. So we're working on 2 diagrams for this. Anov has taken this diagram. He and I have split this up. He's doing the software for the axes. I think he's finished that. I'm working on the plot. I haven't quite finished that. We will put it together, and then you will end up by being able to extract that into CSV. And we'll also do the same thing for this Exaf's and Zane's plot here. So that's it. Here are some of the things I think of values. We can do semantic search. We can validate our data, find out how variable it is. We can do aggregation and systematics. We can do knowledge prosthetics. By that, I mean, if you've got a subject you don't know about, then you can automatically ask the system, what does Zane's mean? You know, what does MSE mean? And things of that sort. And we can start to ask new questions. So that's it. I thank very much NIPGR, National Institute for Plant Genome Research in Delhi. And here are some of the tools which we put on the web.